So the projection of uniform circular motion and diameter is SHM. So here I am considering a particle is moving on the circumference of the circle of radius A with center O with speed V, and it is moving in anti-clockwise direction. So here particle is initially at X point and it moves towards Y, then X dash, then Y dash, and finally it is X. So moving in the anti-clockwise direction with center as O, and the radius of the circle is A. So the particle is initially at a X point, and after t time, t seconds, it is shifted to P point. It is shifted to P point C. Initially at X point and shifted to P point. And the angular displacement covered by the particle is theta here. And the position of the particle is now at P. Then from point P, draw a perpendicular on y dash, that is N. Foot of the perpendicular is N and Pn is the normal drawn onto the vertical diameter. Now as the particle moves from X to Y, the foot of the perpendicular moves to O to N. O to N. The foot of the perpendicular moving towards Y. If it is moving towards Y, then the foot of the perpendicular is Y itself. Means as the particle moving towards from point X to Y, the foot of the perpendiculars shifted to O to Y. O to Y. Then as it further from Y to X dash, then X dash to Y dash, the foot of the perpendicular shifted to Y to O and O to Y dash. And if the particle moves from Y dash to X, then the foot of the perpendicular shifted from Y dash to O again. Means as the particle moves or completes one revolution, that is in anti-clockwise direction, X, Y, X dash, Y dash, X, this path, then the foot of the perpendicular moves from O to Y, Y to O, O to Y dash, and Y dash to O finally. Means the foot of the perpendicular completes one oscillation along the vertical diameter. The particle makes one vibration or one rotation. The foot of the perpendicular makes one oscillation. So finally we can conclude that the projection of uniform circular motion on a diameter of a circle is simple harmonic motion. So how we can conclude that? So see here, the particle is at P, then the foot of the perpendicular is O. If the particle is at P, then the foot of the perpendicular is N. If the particle is at Y, the foot of the perpendicular is Y itself. Then if the particle is at X dash, the foot of the perpendicular is O. And if the particle is at Y dash, the foot of the perpendicular is Y dash. And if the particle is at X finally, then the foot of the perpendicular is O again. Means the particle is moving from X to Y, then Y to X dash to Y dash, and Y dash to X. Means one complete rotation. So during this one complete rotation, the foot of the perpendicular moving from O to Y, Y to O, O to Y dash, and Y dash to O, means one complete oscillation. As the particle makes one complete rotation, the foot of the perpendicular completes one oscillation. So this is called simple harmonic motion by the projection of the particle on any of the diameters. So finally we can conclude that the projection of a uniform circular motion on a diameter of a circle is simple harmonic motion. Then we go for the displacement in SHM. The distance travelled by the vibrating particle at any instant of time t from its mean position is called displacement. The distance travelled by the vibrating particle at any instant of time t from its mean position is known as the displacement. When the particle is at P point, the displacement of the particle along the y-axis is y. Let us take it is y. If the particle is at P, then the displacement from the mean position is y. Then from the triangle OPN, sine theta is equal to ON by OP. ON by OP means opposite by hypotenuse. ON is equal to OP sine theta. Where here ON is the y. The value is y, the displacement from the mean position. Here OP is the diameter or the radius, it is radius of the circle, that is A. So y is equal to OP sine theta, nothing but y is equal to A sine theta. But theta is equal to omega t. Theta is equal to omega t. So y is equal to A sine omega t. where A is the radius of the circle. Nothing but A is called as the maximum displacement for the particle. So maximum displacement of the particle is called as amplitude. The amplitude of the vibrating particle is defined as the maximum displacement from the mean position. So finally, what is the formula for the displacement of the particle executing SHM? So it is y is equal to A sin omega t. So here the displacement of the particle is y is equal to A sin omega t plus phi. Here y is the displacement from the mean position, A is the amplitude, omega is angular velocity, t is time, phi is phase. So phase indicates the initial position of the particle. Here the initial position of the particle is at mean position, so phi is equal to 0. Suppose if it is initially at a point P, then we have to add the initial position of the particle as some phi. Phi indicates the initial position of the particle. So in this session, we discussed the periodic motion, simple harmonic motion, projection of the particle means the uniform circular motion is SHM, and displacement of the particle in SHM. So first of all, the periodic motion is the motion which repeats regular intervals of time is called periodic motion. So we discussed some examples for this: the rotation of Earth around its axis, the rotation of Moon around the Earth, and revolution of Earth around the Sun, the beating of our heart, the ticking of clock, the bob of the pendulum, vibrating tuning fork, bouncing ball, and a rocking chair. Simple harmonic motion is defined as a periodic motion of a point along the straight line such that the acceleration is always towards the fixed point in a line, and it is proportional to the displacement from that point. So, for simple harmonic motion, the examples are the motion of the cradle, the motion of the needle in sewing machine, the cork floating on water waves, motion of the prongs of the tuning fork, motion of pendulum clock, the motion of simple pendulum, oscillations of violin string, and the motion of the loaded spring. So these are the examples for SHM. And there are some conditions for SHM. They are: motion should be periodic, the object must move to and fro about the mean position, acceleration must be directly proportional to displacement and is towards the mean position, restoring force acting on the body always directed towards its mean position, and finally acceleration displacement must be opposite to each other. So here, to explain these conditions, I am considering one example here. So see the spring. So this is the loaded spring. So here the force applied on the spring such that it makes oscillations. There is a to and fro motion or compression and elongation of the spring. Here the center diagram indicates the mean position, and the first one is elongation in the spring, and the third diagram is the compression in the spring. So when we apply the force on the body, the spring will be compressed and elongation will be continuously takes place. Means the spring makes to and fro motion. To and fro motion means it is repeating at regular intervals of time. So it is periodic motion. Then for every particle, for every body, when we apply some force on the body, the restoring forces developed inside the body, and these restoring forces are tries to regains its original size and shape. So here also the spring, in the spring, restoring forces will be developed. So observe the figure here. In the first diagram, the spring is elongated. So restoring force is acting. It is pointing. The blue color mark is there, arrow. So it is pointing towards the mean position. Means it is trying to regain its original size. It tries to regain its original size. So the restoring force acting towards the mean position. And if you observe the third diagram, there is a compression in the spring. So the blue color mark arrow C, it is means it is directed towards the mean position. So restoring force is developed. It is always towards the mean position. Why it is always moving towards the mean position? Means it is tries to get its original size and shape. That is the purpose of the restoring forces for every body. So the periodic in motion and the restoring forces, it is periodic in nature, and restoring force always acts towards the mean position. Two conditions are satisfied by this loaded spring. And if you observe the acceleration is also directed towards the mean position. The force is acting towards the mean position. We can say that acceleration is also acting towards the mean position. And we can see that by the application of force only there is a displacement in the body. Means the acceleration always proportional to displacement. Acceleration is always proportional to displacement. And if you observe the acceleration and displacement's directions, both are opposite to each other. Both are opposite to each other. If it is along the towards the mean position, the displacement is away from the mean position. The third diagram, it is moving towards the mean position, restoring force or acceleration, but the displacement is away from the mean position, like this. So acceleration, displacement must be opposite to each other. So these are the conditions. Now the projection of the uniform circular motion. So here, to explain this, I am considering a particle is revolving in the circular path. So it is at point X and it is moving in the direction X, Y, X dash, Y dash, X. And I am considering the particle is moving to a point P, shifted to point P in t seconds. Initially it is at x and it is shifted to point P. So, and I am considering two diameters here, x dash and y dash, and O as the center. So here the angular displacement covered by the body is theta here, and where theta is omega t. So angular velocity is omega, and it is the linear velocity of the body is v. Now the particle is moving from x to y, y to x dash to y dash, and y dash to x. So to explain this concept, I just drawn a normal Pn on the vertical diameter y dash. Here n is the foot of the perpendicular. And if the particle is at x point, then the foot of the perpendicular will be O, and the normal is xo. Normal is xo, and the foot of the perpendicular is O. So here the particle is moving from x to y, then the foot of the perpendicular is shifted from O to y, and it is the particle is shifted from y to x dash, the foot of the perpendicular is shifted from y to O. As the particle is shifted from x dash to y dash, the foot of the perpendicular is moving from O to y dash. And finally, if the particle is moving from y dash to x, the foot of the perpendicular is moving from y dash to O. So as the particle is completes one rotation, the foot of the perpendicular makes one oscillation. Means there is a to and fro motion about the mean position. So this is the simple harmonic motion. The displacement in SHM. So to explain the displacement in SHM, I consider the same concept here. The particle is moving in the circular path in x, y, x dash, y dash, x anti-clockwise direction. And here the particle is moving from x to P point in t seconds. Means the displacement of the foot of the perpendicular is from mean position is y. Here the particle is moving in the circular path, but the foot of the perpendicular is only executing SHM. So I am concentrating on the movement or position of the foot of the perpendiculars only. The foot of the perpendicular is making simple harmonic motion. So consider the displacement of the foot of the perpendicular from the mean position. So what is the foot of the perpendicular position? It is at n. When the particle is at P, the foot of the perpendicular is at n. And what is the displacement covered by the foot of the perpendicular? It is y from mean position O. So the displacement of the particle executing SHM is y. Now we are going to find the expression for y. To find the expression for y, I am considering this a triangle. There is a triangle formed, that is OPN is a triangle, and theta is the angular displacement theta. So I am considering the sine, the trigonometric ratio sine theta. It is opposite by hypotenuse, that is ON by OP. We know that ON is the displacement from the mean position, that is y, and OP is the radius of the reference circle, that is A. So sine theta is equal to ON by OP. ON is equal to y. OP is equal to, so OP is equal to A. So ON is equal to OP sine theta. So y is equal to a sine theta, but theta is equal to omega t. So finally, the displacement of the vibrating particle or executing SHM y is equal to a sine omega t. Here small a is the maximum displacement of the particle executing SHM in this case. So y is equal to displacement and a is the amplitude and omega is the angular velocity, t is the time. So if we consider the initial position of the particle, then we consider as the displacement of the particle is in SHM y is equal to a sine omega t plus phi. Suppose omega t plus phi is equal to 0. Omega t plus phi is equal to 0. Then sine 0 is equal to 0. Then y is equal to a into 0. The displacement is 0. Omega t plus phi is equal to 0. Then displacement is equal to 0. Means the particle is in the mean position. Omega t plus phi is equal to 0, nothing but the particle is in the mean position, so there is no displacement. If omega t plus phi is equal to 90, then what happens? Y is equal to a sine 90. Sine 90 is equal to 1. Y is equal to a into 1. So it is a maximum displacement. Maximum displacement is a. Means the particle is at the extreme position. At the mean position, the displacement is 0. At the extreme position, the displacement is a. The maximum displacement is a. So depending on the values of omega t plus phi. So whereas omega is the angular velocity, t is the time, phi is the phase. If we consider the total term omega t plus phi, by substituting the values of these omega t plus phi, we can get the values of the displacement at the individual positions of the particle. At every position of the particle, we can get the displacement of the particle just by substituting omega t plus phi. So this is the displacement of the particle. Y is equal to a sine omega t plus phi. Y is displacement, a is amplitude, omega is the angular velocity, t is the time, phi is the phase which indicates the initial position of the particle. So this completes my session today. Thank you.